Topic 15, Part 2, Temperature and Pressure in terms of molecular motion. Temperature of a gas. You just have to memorize these two important points. First one, kinetic energy is the energy the molecules have because of their motions. So these are called molecular kinetic energy. Temperature is a measure of the average kinetic energy or the average speed of all the molecules in the material. Relationship between temperature and kinetic energy of gas molecules. Point 3. At higher temperatures, molecules move faster and have greater kinetic energy. Point 4. The kinetic energy of the molecules is proportional to the absolute temperature. Pressure of a gas. The molecules of a gas are in constant random motion and frequently collide with each other and also collide with the walls of any container. Important points. This diagram here illustrates the random motion of gas molecules. Pressure of a gas continued. Next bullet point. As the gas molecules collide with the walls of a container, the molecules impart a force perpendicular to the wall. The sum of the forces of all the molecules striking the wall divided by the area of the wall produces pressure. Remember, pressure is force divided by the area. This experimental setup is for studying the relationship between temperature and pressure of a gas at constant volume. The gas in this case is simply air in this enclosed flask. The volume of this flask remains constant, and this pressure gauge is for measuring the air pressure. The thermometer is for measuring indirectly the temperature of air, which presumably is about the same as the temperature of water. Explanation. For a constant volume of gas in a sealed container, the pressure of the gas is directly proportional to its temperature in absolute scale or Kelvin scale. When the temperature is increased, the gas particles move faster and have a greater kinetic energy. They have more collisions with each other and with the walls of the container. The pressure is thus increased. This relationship between pressure and temperature at constant volume is illustrated in graphical form. Now we look at the relationship between the volume and the pressure of a gas at constant pressure. As the volume decreases, the gas molecules strike the container's walls more frequent, and thus the pressure increases. This is illustrated by this graph here. We have here a fixed mass of gas inside this cylinder, and as the gas is compressed, the volume decreases, but the pressure increases. Explanation for the relationship between pressure and volume at constant temperature. For a fixed mass of gas at constant temperature, the volume is inversely proportional to the pressure. In other words, the volume multiplied by the pressure is a constant. In terms of formula, P times V is a constant. Or we could say P1 times V1 is equal to P2 times V2. This is a graphical form of illustrating the inverse relationship between volume and pressure at constant temperature. Here is an example. A bubble of air of volume 1 cubic centimeter is released by a deep sea diver at a depth where the pressure is 4 atmospheres. In other words, 4 times the atmospheric pressure. Assuming the temperature being constant, what is its volume just before it reaches the surface, where the pressure is just 1 atmosphere. Use the formula, walk through, the answer to be 4 cubic centimeters.